In this video, we're going to talk about cross products of vectors. Now, before we can talk about cross products, we have to talk about determinants of matrices. So the determinant of a 2 by 2 matrix, so this has two rows and two columns. The 2 by 2 matrix ABCD is denoted by this. Now notice the notation is slightly different between here and here. This is a matrix. Okay, and this is the determinant of that matrix, right? These are like absolute value symbols. These ones have these little notches at the top and the bottom. Okay, it's defined by this. So the determinant of this matrix, ABCD, is AD minus BC. So A times D minus B times C. Okay, so what's the determinant of the matrix 3, 2, 4, 7? So the determinant, it would be 3 times 7 minus 2 times 4. So it'd be 21 minus 8, which is 13. Okay, so the determinant of a matrix is a number. Okay, now the determinant of a 3 by 3 matrix. So that was how to find the determinant of a 2 by 2 matrix. And any 2 by 2 matrix, you can find the determinant using this formula. But how would you find the determinant of a 3 by 3 matrix? And there would also be determinants of 4 by 4 or 5 by 5 or 6 by 6 matrices, but we're not going to get into those. The matrix does have to be a square matrix, though, before you can talk about determinants. So you can't talk about the determinant of a 3 by 4 matrix, let's say. Okay, but for a 3 by 3 matrix, it's a little trickier to find the determinant. One way to do it is this. So we have this matrix, A, B, C, D, E, F, G, H, I. One way to do it is to do what's called expanding along the top row. So what it means to expand along the top row is you're going to think of a plus in this spot, and then a minus here, and then a plus there. So what you're going to do is do plus A times the determinant of, well, kind of omit the column and the row that A are in and look at the remaining matrix. So you look at A times the determinant of the matrix E, F, H, I. Then you end up doing minus B. So again, I said you do plus, minus, plus. You do minus B times the determinant of, well, which matrix? Well, delete the column. Columns are vertical, by the way, right? Like the columns of a building. Delete the column and the row that B is in, and what you're left with is D, F, G, I. Okay, so do B times that. Then finally do plus C times the determinant of the matrix D, E, G, H. Okay, now there's other ways to do it. You could find the determinant the same way, using expanding along, say, the second row or the third row, or you could expand along a column. The thing you have to keep in mind, though, is that the pluses and minus alternate throughout the matrix. So you do plus, minus, plus, then this would be a minus, plus, minus. This would be a plus, minus, plus. But anyways, that's not important. The easiest way to do it is to just expand along the top row like we've done here. And then, of course, the determinant of the matrix E, F, H, I is just E times I minus F times H. And so you can work this out. In fact, you could even distribute the A here and get some final formula here for what the determinant of the matrix is. But I don't remember it based on what the final formula is. I just remember it just based upon expanding along the top row. Okay, so let's do an example. Let's find the determinant of this matrix. We're going to do 7 times the determinant of the matrix 3, 0, minus 1, 5. Then minus 2 times the determinant of the matrix 4, 0, 2, 5. So again, we've deleted the column and the row that 2 is in. And what we're left with is 4, 0, 2, 5. And finally, we'll do 8 times the determinant of, well, delete the column and the row that 8 are in, and you're left with this matrix, 4, 3, 2, negative 1. Okay, and if you work this out, you end up getting 7 times 15, right, because it's 15 minus 0, minus 2 times, well, this would be 20, because it's 20 minus 0. And then plus 8 times, well, this would be minus 4 minus another 6, so that'd be minus 10. So what we get is 105 minus 40 minus 80. That ends up being negative 15. And the determinant of a matrix could be negative. Okay, so there's nothing wrong with that. Okay, one theorem about determinants is if two rows of a matrix are the same, it turns out the determinant will be 0. So if you have two rows, or actually two columns, okay, that are the same, you can check, and it's not too hard just based on the definition, if you think about it a little bit, to check that the determinant will be 0. Another fact is that interchanging any two rows of a matrix makes the determinant switch signs. Okay, so from positive to negative or vice versa. So for example, if I were to switch the second row and the third row here and put the 2, negative 1, 5 in the second row and the 4, 3, 0 in the third row, the determinant would have ended up being positive 15. Okay, by the way, the same thing as if you interchange any two columns, it'll also have that effect as well. Okay, and again, you can think through the definition, think about why that's the case. Okay, now why have we been talking about determinants? Well, cross products, the way we define cross products, we use determinants as kind of a mnemonic device for how to remember how to do a cross product. Okay, so if U is a vector U1, U2, U3, and V is a vector V1, V2, V3, if these are vectors in 3 space, then the cross product U cross V is defined to be a certain vector here. Now, one thing I want to point out is these are vectors in 3 space. You can only talk about the cross product if you have vectors in 3 space. You can't talk about the cross product of 2 vectors that are in 2 space. Okay, or 4 space if you're to do that, right? They have to be in 3 space. Okay, it turns out the cross product is defined by this. Now, don't remember this. This is a messy looking formula. Okay, the way to remember it is like this. Okay, oh, by the way, what this means is the determinant of this matrix times I minus the determinant of this matrix times J plus and so on. So, but a useful mnemonic device to help you remember this formula is that U cross V is equal to the determinant of the matrix IJK, okay, along the top row, and then U1, U2, U3, so take the vector U, put it here, take the vector V and put it in the bottom row, V1, V2, V3. If you calculate this determinant, that will give you the cross product. Now, it's not technically a determinant because the I, J, and K aren't really numbers. Okay, the U1, U2, and U3, V1, V2, V3, those are all numbers. These aren't numbers, these are vectors. Okay, but this is a kind of a mnemonic device for how to remember it. Okay, and that's really where this formula comes from up here. So let's do an example. Suppose U is the vector 1, 2, minus 2, and V is the vector 3, 0, 1. Okay, what is U cross V? And then also, what's V cross U? Okay, now U cross V, we're going to put I, J, K along the top row. Then we're going to put U here, 1, 2, minus 2, and V in the bottom row, 3, 0, 1. So what's the determinant? Well, it would be I. Now I'm going to put, instead of I at the beginning here, we'll put I at the end here, but I times the determinant of this matrix. Okay, 2, negative 2, 0, 1. And then minus, remember it's always minus when you're doing the determinant with the second one here. Okay, we have minus J times the determinant of 1, negative 2, 3, 1. And finally, plus K times the determinant of this matrix here, 1, 2, 3, 0. So notice what it is here. This would be how many I? Well, we have 2 minus 0, that's 2I. Minus, well, how many J? Well, notice we have 1 minus a negative 6. So that would be 1 plus 6, which is 7. Okay, but then we still have this minus in front. And finally, what we have is 0 minus 6. That would be negative 6. Okay, minus 6k. So notice it's the vector 2 minus 7 minus 6, or 2i minus 7j minus 6k. Okay, so notice that when you take the cross product of 2 vectors, your final answer is a vector. Okay, for dot products, the dot product of 2 vectors is a number, right, a scalar. But the cross product of 2 vectors in 3 space is a vector, okay, in 3 space. Okay, now what if we did V cross U? Well, it turns out if we did V cross U, notice what's going to happen is the second and the third row are going to get flipped. So remember what we said, what happens when you flip 2 rows of a matrix, you end up getting the negative of the result. So you can work all this out, but you end up getting the negative of this vector. So you get minus 2i plus 7j plus 6k. Okay, so an important fact here is that U cross V ends up being the negative of V cross U, because ultimately what you're doing is just flipping those 2 rows, and flipping 2 rows of a matrix has the effect of making the determinant become negative, right? Changing the sign of the determinant. Okay, so that's what I've just written here. If U and V are vectors in 3 space, U cross V is the negative of V cross U. Okay, now notice, this is what I've just mentioned here. The cross product is only defined for vectors in 3 space, not 2 space. And the cross product of a vector with itself will be the 0 vector. Now, why is that the case? Well, if you do the cross product of a vector with itself, let's say 1, 2, minus 2 with itself, you'd have 2 rows of this matrix being the same. And remember, we said that if you have 2 rows of a matrix being the same, the determinant will be 0. Okay, so you end up getting the 0 vector. Okay, so if you think that through. Okay, now also the dot product of 2 vectors is a number, like I mentioned here, but the cross product of 2 vectors is a scalar. Okay, a few additional properties, and you can kind of check these for yourselves. Some of these are a little more tedious than others to check. But if u, v, and w are vectors in 3 space and k is a scalar, then the first one we've already mentioned, v cross u is the negative of u cross v. But we also have a type of distributive property. U cross v plus w ends up equaling u cross v plus u cross w. Okay, so you kind of distribute the u there. We also have a distributive property on the other side. U plus v cross w is u cross w plus v cross w. And then if you multiply by a scalar, so if you do u cross v and do this scalar multiplication of that vector with k here, that's the same thing as if you had done ku cross v or u cross kv. Okay, and any vector cross the 0 vector is the 0 vector. Okay, in either direction, u cross 0 or 0 cross u ends up giving you the 0 vector, and a vector cross with itself gives you the 0 vector. Okay, now I want you to remember these cross products. So you can actually, since I is a vector, remember it's 1, 0, 0, and j is a vector in 3 space, it's 0, 1, 0, you can do cross products of these vectors. Now it turns out that I cross j is equal to k. Okay, j cross k is equal to I. Now, notice if you did I cross j, you get k. J cross I would be negative k. Okay, so it's kind of hard to remember, okay, when do you get the positive, when do you get a negative? So here's what I think of. I think of this picture. So I just draw 3 dots, and I draw I, j, k, kind of clockwise here. Okay, I, then j, then k. And I draw these arrows going in a clockwise fashion. It turns out if you do I times j, you get k. Okay, if you do j times k, you get I. And if you do k times I, you get j. Now, if you go backwards, you get the negative. So if you do j, and I said times, but I mean cross, j cross I, you get negative k. Okay, if you do I cross k, you get negative j. And if you do k cross j, you get negative I. Okay, so if you go forward like this, you get the positives, right? I cross j gives you k, and so forth. But if you go backwards, okay, j cross I ends up giving you negative k. Okay, so that's the picture I use to remember these. Okay, now why are these true? Okay, let's just show that I cross j is equal to k. Okay, well, what's I cross j? Well, remember along the top row, we have to put I, j, k. Then we're going to put I right here in the middle row. Okay, I was 1, 0, 0, and j is 0, 1, 0. What if we do the cross product? Well, notice what we'll get is I times what? Well, it'd be the determinant of this matrix, but the determinant of this matrix is 0 minus 0. Okay, so we get 0i. And then minus, well, how many j? Well, cross out this, or delete this column and this row. It'd be the determinant of 1, 0, 0, 0, but that would just be 0 minus 0 again. And finally, we have k times the determinant of this matrix, but the determinant of this matrix is just 1 minus 0, so it's 1. So notice we end up just getting 1k, which we also just call k. Okay, so I cross j is k. And you can check that for all of these right here, that these formulas work. Okay, now, is it true that u cross v cross w is the same thing as u cross v cross w? Okay, it turns out it's not the case. Okay, so cross products are not associative. Okay, and one quick example where you could see this is if we did I, j, j, you could do it 2 ways. You could do I cross j, or you could do I cross j cross j. And it turns out you're not going to get the same answer. In fact, if you do the first way, I cross j, well, j cross j gives you 0. Any vector cross itself is 0, and I cross 0 is 0. But if you did it this way, well, I cross j is k, and then k cross j gives you minus I. So notice that you don't get the same thing. So by the way, it doesn't make any sense then to write u cross v cross w, because you have to decide, well, do I mean u cross v cross w, or do I mean u cross v cross w? Okay, and so it doesn't make sense to write this. You would have to write it with parentheses like this to indicate what you mean. Okay? All right, now if u and v are vectors in 3 space, it turns out, and this is a very important fact here, that u cross v is going to be orthogonal to or perpendicular to both u and v. Okay, and that's really what this theorem says. If u and v are vectors in 3 space, then u dot u cross v is 0. In other words, u is orthogonal to u cross v, or u cross v is orthogonal to u. And the second part B, says that u cross v is orthogonal to v, right? V dot this gives you 0. Remember, if you dot two vectors together, you get the 0 vector. That means that they're orthogonal or they're perpendicular. Okay, so I want you to think about why that theorem is true. In fact, I don't want you to just think about why it's true. I want you to actually maybe prove like why part A is true. Okay, and think about how would I even prove that this is true? Well, just write U as say U1, U2, U3, and V as V1, V2, V3, and then compute the cross product U cross V and write it all out. Okay, it's going to be some messy expression involving U1s and U2s and V1s and V3s and U3s all over the place. But then whatever vector you get, okay, it'll be something I plus something J plus something K. Dot that with the vector U, okay, which is really U1, U2, U3, or U1I plus U2J plus U3K. Dot those together, and if you do that algebra, it's just a little messy algebra. Everything should kind of cancel out, and you should end up getting 0 as a result. Okay, so I challenge you to try. If you do it for A, you don't have to do it for B. You can kind of convince yourself it's true. Okay, so now, in fact, let's do an example that really shows that this is true. So remember, we showed that if U is 1, 2, minus 2, and V is 3, 0, 1, so these are the vectors we looked at earlier, we computed the cross product, U cross V, and it ended up being 2, minus 7, minus 6. Okay, so is that vector U cross V, is that orthogonal to both U and V, the original vectors? Well, let's check. Let's do the dot product of 2 minus 7 minus 6. By the way, when we did it, we called it 2i minus 7j minus 6k. But we can write it like this in this bracket notation. So let's dot this with, say, u. So let's do 1, 2 minus 2 dot with 2 minus 7 minus 6. Notice what you get is 1 times 2 is 2, plus 2 times minus 7, that'd be minus 14, plus minus 2 times minus 6, that'd be plus 12. And so notice that ends up giving you 0. And the same thing happens with V dot U cross V. So you do 3, 0, 1 dot with this. Notice you end up getting 6 plus 0 minus 6, which is also 0. So this doesn't prove anything, right? To do the proof, you'd actually have to work it out up here. But at least in the case that we looked at, and there was nothing special about these vectors. I didn't try to rig it up in some way, right? U cross V did end up being orthogonal to both U and V. So here's the picture. And this is a little tricky to draw. Draw these three-dimensional vectors. But geometrically, the previous theorem says that U cross V is a vector that is orthogonal to or perpendicular to both U and V. So if U and V are both vectors popping out from some point. So maybe one way to do this is take two pencils or pens in your hand and have two pencils kind of emanating like a U and a V from some point. Now, they don't have to be at right angles to each other. Okay, maybe the angle between them is 30 degrees or 47 degrees or whatever, 58 degrees or 125 degrees, whatever. Just have two vectors popping out from some point. Those two vectors will lie in a certain plane. There'll be one flat plane that contains those two vectors. The vector U cross V will pop out perpendicular to that plane. So in other words, U cross V will be perpendicular to both U and V. Okay, it's hard to draw this here, so I drew this little box here to indicate it's perpendicular to V. I was trying to draw it for U, but I had to draw a little bigger here to indicate that U cross V is also perpendicular to U. Okay, now it turns out that we use the right-hand rule to determine the direction of U cross V, because there'd actually be, you could have a vector popping out this way, or if it popped out in the exact opposite direction, that vector would also be perpendicular to both U and V. Now, how do you know which way it's going to pop out, this way or that way? Well, if you use your right hand, if you do U cross V, use your right hand so that your palm is right here and your fingers are pointing out this way. And so that if you curled your fingers, they would curl toward the V. Okay, now the direction that your thumb is facing, if you're doing this with your right hand, would be the direction that U cross V is going to be. Okay, now if we did V cross U, your hand you kind of have to contort your hand a little bit. You'd almost have to kind of put it upside down a little bit here so that your fingers are facing along V, and so that if you curled them, they'd curl toward U. The way your thumb would be pointing would be down this direction. That would be V cross U would go down here. So remember, U cross V and V cross U are negatives of each other. They point in the exact opposite direction. Okay, now the one other question we ask is that, well, there's lots of vectors that are perpendicular to both U and V. They would all lie along this same line right here, but how long is the vector going to be? Okay, how long is U cross V going to be? Well, it turns out that the length of u cross v ends up being the area of the parallelogram determined by u and v. So in other words, if you look at u and v, these vectors will determine a certain parallelogram. Remember, these vectors will be a unique plane that contains these two vectors, as long as the vectors are not pointing in the same, u and v aren't pointing in the exact same direction or exact opposite direction. There'll be a unique plane that contains these two vectors. And within that plane, if you draw this parallelogram, the area of that parallelogram ends up being the length of this vector here. So let's suppose that you keep u right here. If you were to kind of take v and keep it v the same length, but kind of bend it more toward u, you'd have a parallelogram that is kind of elongated a little bit, but it would actually have a smaller area. You can imagine v kind of being even real close to u. You get a small area for your parallelogram, so the u cross v would actually be not as long. Okay, now if v starts looking more and more like a right angle that it's going to make with u, then this parallelogram will actually look more and more like a rectangle. Okay, and that area will be bigger, and then u cross v would end up just being the length of u times the length of v, right? Because the area of a rectangle is just the length times the width. Okay, so so that's a key fact. Now, why is that fact true? Now, by the way, we've given a full geometric description now. If we're given u, a vector u, and given a vector v, we know exactly what u cross v is going to be just geometrically, because we know which direction it's pointing in. It's got to be perpendicular to both u and v. And the fact that it's u cross v as opposed to v cross u means it's going to be popping up this way as opposed to down that way. The only question left is, how long is u cross v? And it turns out it's the area of this parallelogram. Okay, so we've given a complete geometric description of what u cross v is. Okay, now another way of stating this theorem, and it's not clear that this is another way of stating that theorem, but another way of stating the above theorem is to say that if theta is the angle between the vectors u and v, then the length of u cross v, now I said the length of u cross v is the area of this parallelogram. Okay, but I'm claiming that the length of u cross v is the length of u times the length of v times sine of theta. So what I'm really saying is that these two things are equal to each other. Okay, I have to prove this. But then I'm also saying that this formula gives us a formula for the area of that parallelogram. Okay, it's not necessarily clear, but let me draw a picture here. So suppose this is the vector u and this is the vector v popping out into 3 space somewhere. So it looks like these are flat in the plane, but these are vectors in 3 space. So the length of, let's draw this parallelogram here. Okay, so we have u and v, and draw this parallelogram. The length of this side is the length of u, the norm of u. The length of this side is the norm of v, right? Because that's the vector v. Now, if we drop a perpendicular right here, so I dropped a dotted line here. One question I could ask is, what is the length of this side right here? Okay, I'm going to call this length b, because it turns out that the area of a parallelogram is the base times the height. And now by height of the parallelogram, you don't mean this length along the side here, you mean this length. Okay, and it's pretty clear that the area of a parallelogram is going to be this length times this length, because notice if you went over here and dropped a perpendicular, if you took this little triangle and moved that triangle to right over here to kind of fill in this blank spot, notice what you would have is your parallelogram would now be a rectangle, right? If you move this piece, kind of cut along this dotted line, move this piece over to here, we'd have a rectangle, and the area of a rectangle is the length times the width, or the height. Okay, and the length would be the norm of u, and the height would be this side that we're calling b. Now ignore that it's the norm of v times sine of theta, because that's what I want to show it's equal to. Okay, but let's call it b. Okay, but what is b? I want to show that b is actually this. Well, notice we have a triangle right here. Okay, a right triangle. We have this angle theta, and opposite of theta we have this side b, and then the hypotenuse here is the norm of v. So actually, sine of theta, shouldn't that be b over the norm of v? Okay, or in other words, b is equal to the norm of v times sine theta. Okay, and that's what I've written right here. Okay, so this height here is actually the norm of v times sine theta. So what is the area of this parallelogram? Well, the area of the parallelogram is the base times the height, but the base is the norm of u, and the height is the norm of v times sine theta. So we just use some simple trigonometry to see that that's that. So notice the area of a parallelogram. So the formula for the area of a parallelogram is this. Okay, now what I still have to show is that, so I've shown that the area of the parallelogram is this. I still have to show that this is equal to this. How can I prove that the length of the cross product is equal to this? So if I show that the length of the cross product, the norm of the cross product is equal to this, what I've really shown is that the norm of the cross product is equal to the area of that parallelogram. Okay, and that's what the theorem up there said. Okay, so why is this true? Well, let's remind ourselves cosine theta is u dot v over the norm of u times the norm of v. So we thus have the area of that parallelogram determined by u and v is given by this formula. Okay, right? That's what we just showed in that picture right above. Okay, now remember sine theta though, sine squared theta plus cosine squared theta is equal to 1. So sine theta is the square root of 1 minus cosine squared theta. Okay, but what's cosine squared theta? It just means cosine theta, that whole thing squared. But cosine theta, according to this up here, was u dot v over the norm of u times the norm of v. Okay, now we can work out some more details here. It's really just algebra the rest of the way. We can pull this underneath the square root, but since this itself doesn't have a square root over top of it, when it pulls in, it's going to pull into something squared. So we take this thing squared and multiply it by 1, and take this thing squared and multiply it by this. And if you work out the details, you do this thing squared times 1, you get this, and then this thing squared times this, well, that will cancel with the denominator here because that's also squared. And you just get u dot v squared. All right, so it's just a little bit algebra, but you pull that inside. And then notice, remember, what's the norm of u squared? Well, that's u1 squared plus u2 squared plus u3 squared. Okay, what's the norm of v squared? It's v1 squared plus v2 squared plus v3 squared. So if we multiply those together, it's going to be kind of a mess, be messy algebra. Then minus u dot v. Well, u dot v is u1 v1 plus u2 v2 plus u3 v3. And then it was u dot v squared, so we have to square that. Okay, we'll multiply all this out. So do this times this, and then do this thing times itself. A whole bunch of things will cancel, and then you can rewrite it in a certain way that it's something squared plus something squared plus something squared. And it turns out that those somethings are actually the components of u cross v. So I kind of omitted some messy algebra here, but you get the idea of how the proof would go. It's just going to involve some messy algebra. I've omitted some steps. You can try it if you want to. But the point is, I've shown that the area of the parallelogram determined by the vectors u and v, okay, is given by this formula, and that's what we showed right here. Okay, the area of this parallelogram is given by this formula. Okay, but then we showed that this formula is actually equal to the norm of u cross v. So what we've ultimately shown is that the norm of u cross v is equal to the area of the parallelogram determined by u and v. Okay, that was a messy sounding little proof there. I'm not going to ask you to recreate this on an exam or a quiz, but the key idea is that the length of u cross v, how long is that cross product vector? It's equal to the area of the parallelogram determined by those two vectors. Okay, so here's another way of drawing this picture. Okay, let's move on. So here's a last question. Actually, we're not quite the last question. We got one other thing left here. But one of the last things is find the area of the triangle. So I'm not asking about area of a parallelogram. Find the area of the triangle having these vertices P, Q, and R. Okay, so where P is 1, 3, negative 2, Q is 3, 7, 1, and R is 2, 8, 3. Okay, so I'm not going to try to draw these perfectly in 3 space, but there's some point P in 3 space, another point Q, and another point R. Now we want to find the area of the triangle determined by those 3 points. So pick any 3 points. Just kind of imagine 3 points out in 3 space somewhere, and draw line segments connecting those 3 points. Okay, and you'll have a triangle. Right? That triangle will lie in a nice plane, right? And the question is, what is the area of that triangle? And again, these are not points in the plane. These are points out in 3 space. Okay, P, Q, and R are points out in 3 space. But those 3 points, if you were to draw line segments connecting them, they would give you a triangle. Okay, now that triangle would lie within some plane. Okay, but the question is, what's the area of that triangle? Well, notice the area of that triangle will be half the area of this parallelogram here. Okay, and we can find the area of this parallelogram by drawing the vector PQ and PR. Okay, I've decided to pick the point P here as my kind of base point. You could have picked R or Q, doesn't matter. But let's look at the vector PQ and PR. If we take the cross product of PQ, that vector, with PR, the length of that cross product will give us the area of this parallelogram. And then we can just take half of that area. It'll give us the area of this triangle. Okay, now that might seem like a kind of a tedious result, but I challenge you to try to find some other way to find the area of that triangle. Okay, good luck, right? I mean, I'm sure there's a way to do it, but I think this is the easiest way. Okay, so what's PQ? Well, remember, the way to find PQ is you subtract the coordinates. You do the coordinates of Q minus the coordinates of P. Okay, so you do 3 minus 1, okay, comma, 7 minus 3, comma, 1 minus the negative 2. So that gives us the vector 2, 4, 3. Do the same thing with PR. Take the coordinates of R and subtract the coordinates of P, okay, respectively. And you end up getting 1, 5, 5. Okay, so what's PQ cross PR? Well, PQ cross PR, we put IJK here. We're going to do the determinant of this. We put 2, 4, 3, and 1, 5, 5. If you work things out, how many I do we have? Well, it'd be 20 minus 15 I. Okay, minus how many J? Well, it'd be 10 minus 3. It'd be 7J, but we have a minus in front of it. And then plus how many K? Will be 10 minus 4. That would be 6K. Okay, so notice that the PQ cross PR is the vector 5, negative 7, 6. Okay, 5I minus 7J plus 6K. Okay, so what is the norm or the length of that vector? And that's going to give us the area of this parallelogram. Okay, well, the length of that vector is the square root of 5 squared plus negative 7 squared plus 6 squared, which ends up giving us the square root of 110. So that's like 10 point something. Okay, it's between 10 and 11, the square root of 110 is. Okay, so that would be the area of this parallelogram. Well, the area of the triangle is going to be 1/2 the area of that parallelogram. So it's 1/2 the square root of 10. That's the area of that triangle. Okay, it turns out it's about 5.244 square units. Okay, that's the area of that triangle. So again, it seems kind of weird that we're using cross products and determinants and matrices and everything where we're just trying to find the area of this triangle. But believe me, I think this is the simplest and easiest way to find the area of that triangle. Okay, there may be some other ways to do it. It's definitely not impossible. There are definitely other ways to do it, but I think this is probably the simplest way. Okay, now one last thing we're going to look at is something called the scalar triple product. And the scalar triple product is defined like this. So if u, v, and w are vectors in 3 space, the scalar triple product of u, v, and w is defined to be u dot v cross w. Okay, so it's not u cross v cross w, it's u dot v cross w. So what kind of a thing do we get as a result? Do we get a vector as a result, or do we get a scalar as a result? Well, v cross w will be a vector, and we're going to do this vector u dot with that vector. But when you do the dot product of two vectors, you end up with a number. So our final answer is going to be a number. Okay, now what is that number? What is that number going to represent? We'll see in a second. But one key thing that's important to note is there's actually a quick way to calculate this. You don't actually have to do v cross w and then dot with u. Okay, the quick way to do this is to just find the determinant of this matrix, u1, u2, u3, v1, v2, v3, w1, w2, w3. If you find the determinant of this matrix, that'll be the same thing as if you'd done the cross product here and then dotted with u. And that's actually not too hard to see if you think about what how we did the cross product with the I, J, and the K. We're just putting the components of u up here with the I, J, K, and that's kind of equivalent to having done the dot product. Okay, if that didn't make sense, don't worry about it too much. The point is there's a quick way that you can compute this scalar triple product. Okay, and then also, what does the scalar triple product mean? Well, we will see in just a second here the significance of it. But calculate the scalar triple product of u dot v cross w for the vectors u, v, and w that I've given here. Okay, well, it turns out we can just make the determinant of this matrix. We don't actually have to do v cross w and then dot with u. We can just put u up here. We do 3 minus 2 minus 5. And then we do 1, 4, minus 4, because that's what v is in the second row. And the third row, we do 0, 3, 2, and it's 0 because there's no I, right? It's 0i plus 3j plus 2k. Okay, and if you work out the details, turns out that you get 49 as a result. Okay, you do these matrices and these determinants. So you do 3 times the determinant of this matrix minus a -2 times the determinant of the matrix 1, -4, 0, 2. And finally, plus a -5 times the determinant of this matrix, 1, 4, 0, 3. If you work it out, you get 49. Okay, now the last theorem here, and I'll have a picture for you to see here in a second, is let u, v, and w be vectors in 3 space. It turns out that the volume, v, of the parallelepiped that has u, v, and w as adjacent edges is the absolute value of the scalar triple product. That is, v is the absolute value of this. So let me show a picture here. Okay, we have the scalar, this is just a website I found. The scalar triple product of vectors in 3-dimensional space. So notice it's defined the same way I just told you how it's defined. It says geometrically the absolute value of the scalar triple product is equal to the volume of the parallelepiped determined by the vectors u, v, and w as depicted here. So notice here's u, here's v, and here's w. Basically these 3 vectors all popping out from the same point. Notice these 3 vectors determine not a parallelogram, so u and w, or u and v, those would determine a parallelogram, or v and w and v, that would determine a parallelogram. But the 3 vectors all together, they determine this, what's called parallelepiped. It's kind of like a box, but the box is sort of slanted over on its side a little bit. I guess if u, v, and w were at right angles to each other, then this would be an actual box. Okay, but this is called a parallelepiped, and it turns out the volume of that parallelepiped is just the absolute value of the scalar triple product. Now, the scalar triple product could end up giving you a negative number, like -19 or something, but that's fine. The volume would then be +19. Okay, so it turns out that in this problem that we just looked at here, if we were to actually draw these vectors, u, v, and w, out in 3 space, okay, look at the parallelepiped determined by those 3 vectors, and I'm not even going to attempt to draw it here. That volume of that parallelepiped would be 49 cubic units. Okay, 49 units cubed. Okay, now, by the way, notice what would happen. Could that parallelepiped kind of break down? Well, it turns out that u dot v cross w could be 0, but that would only be true if and only if u, v, and w lie in the same plane. So let's go back to our picture. So notice that v is popping up out here. Imagine v, so keep u and w the same. Imagine v kind of bending over on its side so that the box is kind of leaning over further and further to its side. Well, what if v moves all the way so that it's in the u-w plane? Well, then that box has kind of degenerated, so it doesn't really have any height to the box, right? It's just all flat in the plane. Well, what's the volume of that parallelepiped? Well, it's 0, right? And so notice that u, v, and w will all lie in the same plane if and only if their scalar triple product is 0, right? The volume of that parallelepiped is 0. So that's one quick way of showing whether 3 vectors will all lie in the same plane, right? 3 vectors that emanate out from do they all lie in the same plane? Well, that would be the case if and only if their scalar triple product is 0.